All right, Mr. Hambley here. We're going to go through your solubility rules and precipitate lab. So I'm here in the lab. You guys are at home. Let's go through, grab your worksheets, and safety first. Let's get at it. Before we begin, we need to talk about the process of dissolving. So if I take a solid chunk of sodium chloride and take that solid chunk, remember that solid chunk is made up of ions, right? A whole lattice structure of ions. And if I put this into water, what actually happens? These things break apart into its ion forms. We call this dissociation. So the sodium breaks off into its 1+ ion, and the chloride breaks into its 1- ion. Okay? What happens on a particle level here is these ions get totally surrounded by water molecules. So remember, water is a charged molecule where we have a partial negative with the oxygen and a partial positive with the hydrogen. And therefore, these positive and negative ends of the water molecule orientate themselves with the ion. So if this is the negative, the oxygen would surround the sodium 1+ ion, and the hydrogen positives would surround the chloride 1- anion on a particle level. Okay? We can take it even one step further. Here is the PhET simulator salts and solubility online. I'm using still table salt, which is sodium chloride. Now watch what happens. There's a little ion chart up over here. The sodium is red and the chloride is green. When I shake the salt shaker into this water, watch what happens to the ions here. So shake this, nice and slow. Here's a whole bunch of solid salt going into the water. I'll just let this kind of play out here. And as you see, as the solid gets into the water, they dissociate into ions. So again, the sodium and the chloride anion break apart and are dissolved in the water. You can see dissolved, all 42 of these ions are dissolved in. If I shake even more in, you can see that even all of those are going to be dissolved in the solution. So again, this is the process of dissolving. It's a physical change, and we're going to be using this throughout this lab. Here is our worksheet that we'll be working with today. So we are working through solubility rules and precipitates. I'm going to give you a little bit of time. Make sure you pause the video and look up these definitions, either using the textbook section that was posted or just a blanket internet search. So what is a precipitate and what is solubility? Kind of gone over what is solubility a little bit with what is dissolving. Now, we've got a whole bunch of materials here. We've got a whole bunch of cations, and I'm going to be working through this, and you have some discussion questions to answer at the end. If we flip the sheet over, you'll see that there's two strategies to this lab. Okay, we can either start with cations and then add anions, so working our way across this way, or we could start with an anion and just insert all the different cations. I'm going to take the cation approach. So I've got a reaction plate, and what we're going to be doing is just adding anions in. So here's my reaction plate here, and you can see I've started to label all of the different anions that are going to go in each one of these holes of this reaction plate. So this reaction plate has some holes. So here's the orientation here. And what we're going to start with is we're going to put one of the ions, the cations, in each one of these wells. And then what we're going to do is add a drop of each one of these anions into the wells. Okay, let's do this. All right, first up is sodium cation. I'm going to take this and I'm going to place a drop or two in each one of these wells. Now what you're going to be looking for is just evidence of chemical change. So here is chloride. Nothing much there. OH, hydroxide. Much there. Bromide. Phosphate. Iodate, or iodine, sorry. Sulfide. Take the cap off, that helps. Carbonate. And last but not least, nitrate. Now, take a look at all these wells. I picked a clear dish on purpose, reaction plate. I don't see any evidence of chemical change happening whatsoever. Let's go back to our chart and see what happens. So here's our table, our observation table, and we had no reactions for all of these ions. So when we combined sodium with chloride, we had no reaction. NR is what I'm going to write down. We had no reaction with the hydroxide, bromide, sulfide, iodide, phosphate, carbonate, or nitrate. NR all across the boards. Okay, let's move on to potassium. All right, I've done the reaction with potassium here. I've actually pre-recorded all of this, or pre-did it off camera just for sake of time. And you can see here we have no reaction between the potassium and any of the ions that are here. So potassium cation doesn't form a precipitate with any of these anions. All right, next up is ammonia, NH4 with a 1+ charge, ammonium. You can see, pre-recorded, again, this lab is starting off with not very excitement on the precipitate front. So we've added ammonium with all of these anions, and you can see that none of them formed a solid precipitate. Let's move along to the next one on your list, that is lead. All right, lead 2+. Remember, lead can be multivalent, but this is the 2+ cation. For the lead, I've preloaded all of these wells with the anion, the appropriate anion. So here is lead and chloride. Ooh. With hydroxide. Oh, even better. Bromide. Sulfide. Nitrate. Oh, nothing there. Carbonate. So I gotta grab some more here. Ooh. Phosphate. And last but not least, iodide. Ooh, that's the best of the bunch. Make some observations now here. Again, the precipitates that are formed aren't all the same, right? You can tell that this is a super bright yellow color, which is really neat. Some of these have more of a bluish, whitish tinge to them. The only one that didn't react was the nitrate. All right, there is lead 2+. All right, next up is calcium 2+. Calcium 2+. Let's see if there's any reactions with any of these. Here's calcium with chloride, calcium with hydroxide, something, bromide, sulfide, iodide, phosphate, nitrate, carbonate. So you can see we got some observations to make about the precipitate formation with this. Again, calcium 2+. All right, next up is magnesium 2+ cation. Let's see what magnesium cation reacts with all of these anions. Chloride. Ooh, hydroxide. See a little formation of something in that. Bromide. Nothing. Sulfide. Iodide. Phosphate, carbonate, nitrate. It's hard to see, but really small precipitate formations in these two wells. So with the phosphate and the hydroxide. That's been magnesium 2+. Also with the magnesium 2+, I would say that there's another precipitate here. All right, next up is barium 2+. Let's see what barium does when it reacts with all of these anions. Chloride, hydroxide, there we go. Make your observations. Which ones had precipitate formed, and what could you say about those precipitates that do get formed? This has been barium. All right, next up is copper 2+. Remember, copper is also multivalent, but this copper 2+, just to start with, has this nice little turquoise bluish hue to it. So we're looking for it not to turn blue, because that's what it originally is. But here is copper 2+ with chloride, hydroxide, bromide, sulfide, iodide. Ooh, that's nice. Nitrate, carbonate. Now, we've just had this one turn yellow. I believe that this is contamination from a previous experiment. I've been washing and drying off this reaction plate as we do it, but you can see where I'm going to try this one just again with a new reaction plate. Okay, I think it's contamination. So just because our lab looked like there was some contamination of the reaction plate, I'm going to take iodine 1-, so iodide ions, put them in the middle well, and here I've got my copper 2+ as well. Let's give this one little test again to see, because that yellow is kind of weird. So you can see as we mix them, well, it's not. So you can see something here has happened, that we actually didn't have any contamination. I just want to try to get a close-up view of what is happening in this reaction plate. Again, this is iodide, I1-, and I'm going to add some copper 2+ to it. And watch what happens when these things mix. That's just awesome, solid precipitate formation. All right, here is iron 3+, a really old label. You can see this bottle's kind of crazy. I just made up some fresh solution here. This is what iron 3+ cations look like in solution. So it already has this kind of orangey yellow tone. Let's see how it goes when we add it into these anions. All right, we've got some precipitates forming slowly too. So make your observations on your sheet. And that's all of them. So we've got a little bit more things to chat about. Let's chat about some of the questions on the front sheet. All right, the last part of this lab is kind of some trickery that I was doing with the labels. So if you can see here, I've got 2 dropper bottles. This one's labeled Na1+. It's very much like from the video. This one was the anions S2-, so sulfide anion. Now, the tricky part about all of this is that inside of this dropper bottle is not just the sodium ion, okay? So sodium, as we know, is 1+. But with all of the cations has to come an anion. So there has to be some anion, let's label it X, that would have a 1- charge to balance out the sodium, or it might not as well. There could be multiple options to this. And again, remember, these have to be highly soluble. So when I put both of these into a beaker with water, what would be floating around in the solution would be a whole bunch of sodium ions, so Na1+, as well as a highly soluble anion that would have the opposite charge of the sodium, okay? So a whole bunch of these. And again, remember, these are all surrounded by water molecules, water being a polar substance. Same thing goes with these anions. So I can't just have a dropper bottle that has S2- anion in it, so sulfide anions. There is some sort, let's call this Z. There's some sort of ion here, Z, that's coming along for the ride as well. And we know that this has to be positively charged. If it's 1 positively charged, there has to be 2 of them. If Z is 2 positively charged, then there would just be 1 of them. But again, as I throw this into a beaker, it would dissociate or break apart into its ions as well. You need to know this for this question right here, number 3. All of the dropping bottles in this experiment contain both a positive and negative ion. So you have to look at your results and suggest which negative ion is present with all the positive ions. So what would be X in this case here? And as well, what would be Z? What would be the positive cations used in these experiments as well? There's multiple options. Use your observation table from the video to help you with this question. All right, thanks.